Welcome back to Thrive, your go-to channel for transforming health, revolutionizing indoor air quality, and visionary environments. Don't forget to like, subscribe, and leave a comment down below to let us know your thoughts. Here's Simon Witts on what controls the design.
Now, I'd like to introduce Simon. Simon would say a few words about himself, but Simon, as I probably also you've heard me saying this, he's got this amazing ability and kind of a different sixth sense here. So he looks at this room and he would tell you exactly which way air is going, what's the pitch of the air, and so on. Yeah, I'm not joking. We were sitting, that was in Melbourne one day, and the bar, and you were telling going here and then do this. So, but and it is not a joke. The way Simon can understand these things, and I don't think there's anybody else who has the idea.
I think there are, but no. When you've designed enough buildings, when you've done enough CFD work, when you've done enough stuff, you begin to understand what's going on with the air movement in the buildings that you're looking at. Am I supposed to introduce myself? I'm not sure. Yes, I am. Yeah, so Simon Witts, Director of VA Sciences. I'm a building services engineer by training. About 34 years in the industry now, still learning. Spend most of my time designing hospitals. And our focus at the moment, actually, which is interesting, given that energy is one of the things here. Energy is one of the biggest things that we're talking about with hospitals. We're looking at the moment in helping places like the Alfred and the Austin Hospital in Melbourne decarbonise. So getting rid of gas from those facilities. When you talk about 10 megawatts of boilers, it's a bit of a challenge. So that's so the energy of buildings is a big part of my life, big part of what I do. But right, back to the task in hand, which is ventilation. And just generally, I'm going to look at what controls the design. So I'm a designer. I sit with architects, Jeff, and they come up with a blank sheet of paper, come up with a sketch. This is what we want it to do. Basically, the architect makes it look nice. The civil and structural engineers make sure it doesn't fall over or sink, and the building services engineers make it useful. So, I want you to think about this just a second. Now, it's your turn to work for this. So, 2 minutes. That's all. How many different ways do you use air in a building? Now, I'm using that phrase deliberately. I'm sure Brock could tell us straight away because his building uses air in some fantastic ways. But how many ways do you think we use air in a building? Give me some ideas. No, don't show the answer yet.
Seven.
I wanted to do something. Okay, you had a sneak peek. Who could read quickly? Come on. Heating, yes.
Is there ventilation? Ventilation.
Well, ventilation is a broad term.
And then just
ventilation is the movement of air through the building. But what am I doing with that air? I'm cooling with it. I'm heating with it. I'm controlling humidity in the case of box building. 1%. And by the way, that carrier humidification system, air conditioning system, 1904, as Brock said, air conditioning wasn't invented until 1950 by both both Carrier and Trane. And Carrier at the moment are also probably one of the leading manufacturers in the world of heat pumps, which is the next generation of what's going on there. So really interesting to see what they've got there at the museum. So we use air for cooling, heating, humidity, odor control, contamination, and fire management. That's actually what we use it for. Next slide. And the air itself, this should run. Do we not, yeah, should hit play. This is, for those of you who really like your sciencey stuff, a psychometric chart. And this is how we can work out exactly what the air is doing. The big red triangle diamond thing is the outside air. And all the dots are individual rooms within the space. And with the building management system and the design of the air conditioning system, we're playing a game of trying to keep the dots in the blue box. Most of the time we manage it, some of the time we don't. And some of the times the users decide they want something completely different and want to have it completely different anyway. So I think there's one dot all the way off to the right-hand side because they wanted it as a warm space. So the air in the building, and we are doing all of that control using air, because we want the comfortable building. In this particular instance, it's an animal house, so we actually want to control the environment that the animals are in very closely. And so a lot of effort is being put into the control of the air system to achieve that. And the outside air, the air quality part of it, is actually only a very small part of the amount of air we actually have to move through the building to control the environment. So it's quite a challenge. So, next slide. What are the current rules around the air we use in buildings? Probably going to have to, that's it, good. There really are only 4 or 5 things that we have to deal with in terms of legislation or regulation. And that's the National Construction Code, and then the Australian Standard 1668. So part 1, 2, 3, and 4. Part 1's fire and smoke control, because that is another big thing that we do with air in the building. Make sure it's safe and we can evacuate people and get them out. And again, it's another task that the ventilation system has to perform, on top of all the other things we're asking it to do. 1668 Part 2, mechanical ventilation in buildings, probably the main one that we need to deal with. Part 3 is another one to do with fire and smoke. And then Part 4, natural ventilation in buildings. Personally, if you get a naturally ventilated building, in my opinion, you're not interested in ventilation. You've got other drivers. Next slide. So, of the list that we've got there on the slide, so cooling, heating, humidity control, odor control, contamination, fire management, which is the main driver of the ventilation system? Next slide.
Building top.
Cost.
What's that?
I thought you should watch it.
Cost is the main driver. And unfortunately for us, if you didn't, just the next bit, unfortunately for us, the system type has almost already been decided for us. Before I even get to start designing the ventilation system or designing the building services. Because most of the time, a developer will want a building. That developer, I mean, back in the good old days, the developer would go to an architect who would come up with a scheme. They'd then talk to a quantity surveyor and come up with budgets for this sort of thing. Architects have now almost been pushed to the side by the QS. So the developer will go to a quantity surveyor and say, how much would this 15,000 square meter building cost me? The QS says, oh, it'll be X million. And by definition of that and its type, the building ventilation system is almost already set. If you want to know what I'm sort of thinking about, what I'm saying here in terms of costs, if you're talking about extract only, so just extracting from a building, about $20 per square meter is the budget figure that QS would allow. Supply air, extract air, total system installed from start to finish would be about $90 a square meter. Then move into sort of mixed mode, you're about 120. Then you start to get into the air conditioned type systems. So outside air with a fan coil, DX driven, about $390 to $400 per square meter installed. Outside air full air conditioning, fan coils again, but with chillers, then you're into about the $500 per square meter. And then if you move into the commercial world, with premium grade offices and all the way up to a premier premium grade high rise, you're at about $1,000 to $1,200 per square meter for the ventilation system, which is including the chillers, the cooling, and everything else that you need. So there's a huge range, but that range actually for the building services engineer is very narrow because it's already defined by the cost of the building. So you've got some interesting challenges if you start to look at things like air quality, because you have to look at it through the lens of cost, because that's what's going to happen. Now let's look at the building regulations through that same lens, which we probably don't often do. This is the first regulation in the National Construction Code around ventilation. And can you believe it? It actually says, if you use the room, you've got to ventilate it. They actually had to go to the level of saying, if you're using a room, it has to have ventilation. Why? Because if they didn't say it in regulations, somebody would say, well, it's not required. Next one. Occupants must have appropriate indoor air quality, and all the other stuff. So what I would say is, because I'll go a bit quicker, read the National Construction Code, but read it through the lens of cost. And what you will see very quickly, hold it there, what you'll see very quickly is that it's all to do with minimums. They are the minimum requirement that shall be met. Because if they didn't say that, people wouldn't even try to meet it. Now, here's one of my biggest bugbears with the National Construction Code: the maximum contaminants for indoor air quality. They're there, and a lot of what we're talking about, 850 parts per million CO2. It's within the realm of what we're already talking about as good ventilation and good indoor air quality. Next. No requirements to measure or control any of them. So they've gone to the trouble of saying this is the minimum, and then they say this is it, and then they say, well, yeah, go if you like, you don't have to do anything about it anyway. And as a designer, if I haven't got the need to do it, if I haven't got the brief to do it, I won't do it. Natural ventilation we talked about, standards, yep, keep going. So if you look at AS 1668 Part 2, which is the one concerning ventilation, it really only talks about three things: odor, particulate, and specific gases. But, as I say, we don't measure them. Next one. As a result of that not having to measure it, outside air accounts probably less than 25% of the total air supplied to a building. All the rest of that, the other 75%, I'm introducing or recirculating to help me control temperature, humidity, fire, smoke, environment, whatever. But less than a quarter of the amount of air that I'm putting through a building is actually there for outside air and contamination control. In most of the high-end buildings, we already measure CO2. You'll be glad to hear. You won't like the next bit. As designers, I'm allowed to reduce the amount of outside air that I supply to a building based on the outside air level, or based on the CO2 level. So we measure CO2 so that we can reduce the amount of outside air we're supplying to a space. We don't measure CO2 to increase or improve indoor air quality. And just to give you a sort of quantum of that, in a normal office space, you're talking about one person per 10 square meters and 10 to 14 litres per second per person, depending on what you're dealing with in terms of outside air. So my building design occupancy is one person per 10 square meters. My air change, my amount of air I'm delivering, therefore, is about 10 litres or 14 litres per second per person. When I'm using demand control ventilation, I can reduce that outside air to 0.35 litres per second per square metre, or in that same 10 square metre space, 3.5 litres per second.
We don't measure outside air.
We do. If I'm controlling it, I will do it.
Very few buildings have outdoor airflow measuring stations.
On premium grade offices, we do. And so velocity grids, all the other things. This is where we're up at the $900 to $1,200 per square meter systems. And we also nearly always measure the percentage outside air in healthcare, in the hospital systems, if I'm doing outside air systems. So it's not commonplace by absolute, I completely agree with that. But where the system is designed to do it, and where we're using DCV, demand control ventilation, and in that demand control ventilation, my target is to drive the outside air down as far as I can, because I'm trying to save energy. Then the only way I can actually do it and comply with 1668 is to have things like velocity grids or things like that in DMA.
Yeah, look, I measure it, but I know a lot of people do not measure it.
Yeah, exactly. That's it, really.
This is the bare reality. Nothing is going to happen voluntarily. If there's only $1 increase in price, there's no chance that anything is going to happen voluntarily. So we need standard, we need performance standard, and that's the reality. I was wondering what was happening in this room, because when we came here, CO2 concentration has been going up, and then stopped going down. Whether it was something which you changed to turn it on, and the building didn't know that we are here, and it was going down, and all of a sudden went up when I was going to mention it was below 700. So can't quite understand what's the
CO2, right?
CO2, what the building is.
We're not breathing. Well, what is it?
Well, it was going up and up. Yours is very similar, almost identical. So actually, that's a spatial variation. 879, 871. So, but taking aside this kind of fixation by some of us right now, looking exactly what CO2 is doing. So what I'd like to do is thank you all speakers. And now we'll have a coffee break.